and transcribed, I've noticed, which makes me somewhat self-conscious because the transcription, so here's the transcription of me talking about myself being transcribed. Yeah, this is kind of a weird feedback loop. Okay, what am I doing? I'm looking for that. Yeah, and okay, so we have GeoGebra. I've got a dedicated window for that, and how come that's not showing? Or is it? It is showing. Okay, right. And then I've got the, well, I've got Adobe, but that's a different thing.
Professor, have you taken Roy yet?
I have not,
Or
but
no,
I've said that all the important people are here. So you're here.
Okay, my bad.
For instance, yeah. And this is the, so this is like a whole separate screen, so I can see more clearly what I'm doing. And it makes it a lot easier to navigate because I can just take, for instance, if I take this over there, then, oh no, we're in the infinite tunnel of feedback. Well, let's not do that then. And okay. So over here we can go to class view. So are there any questions about anything? Where do we leave off? Are we going to finish up some loose end? That often is what happens. Okay, was it 2.4? I have my notes here somewhere. Yeah.
I think we basically finished up 2.5.
Yeah, 2.5, huh? Was there?
We had looked at some book examples, but we hadn't looked at like WebAssign examples or anything like that.
Okay, so you want to look at some WebAssign problems from there? Yeah, the book problem, let's take a look at where we left off in the book and maybe, so this is continuity, huh? Oh. Okay. Chapter 2, exercise, this is 2.6, so I want to go back a notch. Okay, so I guess I can go over here and get rid of that. And 2.5, the exercises. And I think we did like 48, right? That was, or 70, was it 48 or? Yeah, 48, right? That was the quiz problem. And it looked like, you know, if you didn't get that, maybe you didn't turn it in, or you did get it and you didn't realize that everybody had to turn it in. So I only got about half the responses. I've only looked at half of them, and of the half I've looked at, only half of them were responses. So maybe next time everybody can do it. So suppose F and G are continuous functions and blah, 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 blah. 51. 52. I'm trying to pick out some here. They're usually the better ones are at the, yeah. So we want to do some intermediate value theorem problems, right? So that's what we didn't do bunch up, right? So 55 through 58, use the intermediate value theorem to show that there is a solution to the given equation on the specified interval. And an easy one like this, I don't even have to write anything down, right? Because the interval is from -1 to 0. So when you're using the intermediate value theorem, you don't have to prove it, right? Because the proof isn't even in the book. So you don't even have to understand the proof. You should have an intuitive idea of what it's saying. And this is another feature of my new situation here, which is I can draw on this screen here somewhat. And I'm still working on my drawing skills, and I have an eraser now, right? Okay, that's great. So, oh, that didn't really come out very straight, did it? Basically, what makes it difficult for me here is that I can't see where my pen is. Okay,
you
so
also have a separate whiteboard in Zoom you can use.
There is a whiteboard. I've never really taken to using it. Maybe I should, huh? In any case, how do you write on the whiteboard? With the mouse, right? I don't like writing with the mouse. So what I've got here is actually a stylus pen. So the idea is if you've got a function that does this, say, right, and we're going from here to there. So this is, let's see, can I write here A, and I'm still having a hard time writing. And this is the x-axis here. And up here we have the y-axis. Don't forget to label your axes. And so this is f of a, right? Oh, well, I don't know why I didn't erase there. And this here is going to be f of b, right? Then so if you got a value n between f of a and f of b, right? So n is between f of a and f of b. And it doesn't matter whether f of a is bigger or f of b is bigger. There just has to be some interval between them. So you can have a number n in between them. Then no matter where I put n between these guys, if it's a continuous function, there's got to be a c down here, right? That will be so that, so given for all n, can I say for all between, I can't write on this thing, f of a and f of b, there exists c, oh, sorry, can I erase that? Yeah, c in the interval from a to b, such that, can I abbreviate such that? There's st, there's also this is an abbreviation for such that, right? That's the sort of logic notation. F of c equals n, right? Okay, so, and you know, try to imagine drawing a continuous curve where that doesn't work. You might say, well, I can do this, right? What's wrong with that? Right now, so that if we're on that curve, we'd be up here, and you know, we wouldn't have an n in between, right? The problem with that is it's not a function, right? It doesn't satisfy the vertical line test. Okay, so the only other way is, you know, you've got this line n, and you're going to get from here to there. What are you going to do? Jump, right? Well, that's a discontinuity. Okay, so I will attempt to learn how to write with this thing on here. All right. So clearly here, f of 0 is equal to what? 1, and f of 1, I think that's the interval, isn't it? Oh, sorry, f of negative 1. Where is my pen? F of negative 1 is, I think that's going to be -2, right? You see that? So 0 is between -2 and 1. So when you're using the intermediate value theorem, all you have to do is establish that the premise of the theorem is satisfied, and so the conclusion must follow, right? And so since we have a continuous function, right? So you should state that, right? F is polynomial. Therefore, it's continuous everywhere, right? So it's continuous. And so f of 0 is positive, f of -1 is negative, 0 is between any negative and positive numbers. So there exists, so, you know, therefore, can we put this, that's the universal therefore symbol, kind of. There exists, this is the symbol for there exists, C on the interval from -1 to 0, such that That's the such that symbol, F of C. And it's just an existence theorem, right? It doesn't say how to find it. Can we find it? Well, that's actually going to be kind of hard here, right? So that's the answer to the question. It doesn't ask for what C is, right? Just that there is such a C. This is an existence theorem. How would you find it? Well, ask Omar Khayyam. He was one of the ancients who talked about how to solve an equation like the cubic equation. In general, there is no cubic formula. Well, there is, but it's not well known, right? It's like nested radicals, and how it's derived is pretty obscure. How about the second one there, natural log x? And let's switch over to the, because I'm obviously terrible at writing at this thing here. Do we have anything in the chat? Insights on the right show you more sample problems so you can see where you struggled on homework. Don't know if you're going to give a practice test. Yeah, a practice test. That's a good idea. I've got like a million of them. So sure. Yeah, don't let me forget to do that. Yeah. So where am I over here? I'm going to be on the DocuCam now, which we can turn up the lighting a little bit here. Okay. And so use the, this is 2.5, number 56. And it says, use the intermediate value theorem to show natural log x equals x minus root x has a solution in the interval from the open interval from 2 to 3. So we want to, so step one is to show it's, find a function, right? We don't have a function at this. We have two functions, one on the left and one on the right, to which we can apply the intermediate value theorem, right? And what function would that be? Right, there's a function on the left and a function on the right. Which one? Well, the trick is to rewrite the equation so that you have a constant on one side of the equation. And why not make that constant 0? You can get that by just subtracting either the left from the right or the right from the left. And I kind of prefer subtracting the left from the right here and then swapping sides. So I'm going to say, look, natural log x equals x minus square root of x is exactly equivalent to x minus square root of x minus natural log x equals 0. Yeah. And so now I can, the function on the left there is what I'm going to apply the intermediate value theorem to, right? Then we want to establish that f of x equals x minus square root of x minus natural log x is continuous on some interval like an interval or subinterval of 2, 3. And by subinterval, so if we're in a subinterval of 2, 3, then we're in that interval, and that will be an answer to the question. Yes, it has a solution in 2, 3. Why would we ever need a subinterval? Well, it could be that, you know, so what's happening here? The closed interval on a closed subinterval. Closed meaning it contains the endpoints, right? And that means it's continuous from the right at 2 and continuous from the left at 3, right? Okay. And can we establish that? Well, is it if it's continuous on this interval, then it'll be continuous on every subinterval, right? Is it continuous on this interval? Well, yeah, it's you know, it's a combination of polynomial, root, and logarithmic functions, right? And these are all continuous functions, meaning that they're continuous throughout their domain. Square root of x does not have all real numbers, neither does as the domain, right? Neither does natural log x, right? So the domain of square root of x is the interval from 0 to infinity, and the domain of natural log x is the interval, the open interval from 0 to infinity, right? And clearly x is continuous everywhere. And so therefore f of x, and these are continuous functions, right? So, and this is part of the domain of those continuous functions. So f of x is continuous on the interval from 0 to infinity, which includes the interval from 2 to 3. So we're good. All right, so step 3 of using the intermediate value theorem is going to say what? Well, you want to find some, I'm going to say find a subinterval, which could be the interval itself, a to b of 2, 3. I should say, you know, subinterval, right? Such that 0 is between f of 2 and f of 3. Well, maybe the 2, 3 will do, right? Is that the case here? So let's make a table of values, shall we? So at 2, we've got f of 2 is, well, it's going to be 2, what's the function up here, right? 2 minus root 2 minus natural log 2, which is approximately 2 minus 1.414 minus 0.693. You all know these. Oops, sorry. You all know these values, right? Natural log 2, is that's a standard number. Why? Well, you know, half-lives and whatnot. The real estate agents call this the rule of 70, right? Because they round up to 70. And 69, you know, the rule of 69 doesn't sound so good. This, you know, something about doubling the value of your house. Good luck with that. So is this positive or negative? This is negative, right? That's really all we care about, whether it's positive or negative. Like, so we're subtracting more than 2 from 2, that's negative. So should we look at 3? Is it going to be positive at 3? 3 minus root 3 minus natural log 3. Well, actually, x is growing fast. This is pretty close to 0, isn't it, right? And x is growing faster than both square root of x and natural log x. So I think, yeah. So I think this will be true. So this is going to be approximately 3 minus 1.73. And what's the natural log of 3? I really need like a hand calculator, don't I? I have one in this. See if it's got batteries in it. This is like seriously dusty, and the batteries are dead. Oh, there is no battery. There are no batteries. Another one in here, I think. What this guy? Probably took the batteries out of this guy too, because yeah, this is the old Voyager 200, anybody? Yeah, those were the days. Okay, well, I guess I don't have that then. Oh, I just used the computer, right? In fact, we can pop into, where is it? GeoGebra? Let's just pop in there for this little calculation here. And for that purpose, oh, I need to have the real GeoGebra. And okay, that cleared out that, didn't it? So this is a slightly different version of GeoGebra. You know, the input line is different and the menus are a little bit different, but that's all right. I just want to compute natural log of 3, right? And that's about 1.1. If I want more digits, sorry, rounding, yeah, like 5 digits, I can get 1.098, but yeah, about 1.1. So go back to here and say this is 1.1, and that is positive, isn't it? Right? So that establishes what we want, right? So 0 is between any negative number and any positive number. It's a pretty close call, right? This is not very negative. This is not very positive, but you know, we got enough information here to establish that, yeah. Therefore, there exists C on the interior of this interval such that f of C is equal to 0, and the equation is true, right? The function is equal to 0 if and only if the equation has a solution. Okay. Questions about that? Oh yeah, Emiliano has the calculator, right? 1.0. I should have just looked at the chat. Right. Okay, I had to paw through my calculator collection. I need a new battery. Now, okay. You're in a field standing next to a mailbox. Those are the Zork days. How about, I don't know, so some of these are a little bit trickier. If you want a really tricky one, yeah, look at this puppy here. Let's try to understand what this is saying. Maybe we'll be able to solve this in the time allotted, but I'm thinking I'll just establish the problem and then we'll maybe come back to it, because I just want you to recognize that this is truly a difficult. Oh, what am I? I'm not looking at. Sorry, I need to be looking at this thing. Yeah. Okay. So this is. So it says if A and B are positive numbers, prove that this equation has at least one solution in the interval from -1 to 1. So let me delve into this a little bit and see just what the problem is, right? So I think pencil and paper time, anybody? Sure. Here we go. So this is 2.5, number 74. The good ones are at the end. Or at the very end of the chapter, there are the good problems as well. So if A and B are in the set of positive real numbers, right, which is what that's saying, right? The set of real numbers is the R, and the superscript plus says non-negative, essentially. So 0 is counted in this set, right? Oh, actually, no. So just to be sure, take away from this the set containing the number 0. So in fact, I don't think we don't want to include 0. It says A and B are positive. That means not 0, right? Strictly greater than 0. So if A and B are positive, prove that the equation, so prove that this equation, which has a couple of rational expressions, one with A in the numerator and one with B in the numerator, and they're added together, right? And so this is x cubed plus x minus 2 equals 0 has at least, can I write that in here? One solution in the interval from -1 to 1. All right. So rational functions, right? So are these continuous functions? So I'm going to call this f of x, right? Let's look, right? So we would have a vertical asymptote if we have division by 0, right? So we want to find the zeros of that denominator and see if they're in this interval, right? That would cause trouble, wouldn't it? Yes, it would. So we want to examine this equation. Does this have real number solutions? Well, yeah, -1 is a solution, right? And that's an endpoint of our interval, right? So it's not continuous at the left endpoint of this interval. It's got a vertical asymptote. Can we find other zeros of this thing? Yeah, we can factor. The factor theorem says if we got a 0, well, we do have a 0, right? -1 is a 0. That means that x plus 1 is a factor. What's the other factor? No, you just guess and check, right? It's got to be x squared to make an x cubed, right? And then if we're going to have a 2x squared here, I think plus x. Right? And then if we're going to have a -1, do we then not have an x term here? Right? Yeah, right, because x times -1 plus 1 times x, those two products cancel out, we get 0, right? And so now we're down to a quadratic. Can we factor the quadratic? Well, look at the discriminant, right? B squared minus 4ac, in this case, that's 5. So what kind of number is 5? Well, it's positive. That means that there are real solutions, but it's not a perfect square, so it's not going to factor without some trouble, right? So I'm going to complete the square and say this is x plus a half squared minus 5/4. Is that right? Yeah. Expand out that square. You get x squared plus x plus a quarter minus 5/4 will be -1, right? So that works. So the other solutions are x equals -1/2 plus or minus, right? Square root of 5/2. And what do we do? Can we approximate those? Just to see if they're in this interval, right? So there's 2, right? One, if you add, and -1 plus the square root of 5/2, and square root of 5 is about 2.45, I think, or 2.44, something like that. So 1.44 maybe, and half of that is 0.72. 0.72 is in our interval, right? Exclamation point, exclamation point. So there's a vertical asymptote on the interior of the interval, right? Pretty close to 1. Well, 0.72 did we say, right? Close to 0.72. So how about the other one? The other one is less than -1, right? Because that's going to be minus √5, so that'll be -3 point something, half of -3 point something. So that'll be less than -1. So we don't care about that one, but we are worried about this one here, right? All right. How about this other denominator? Are we going to have more trouble there? Seems like we got plenty trouble already. So x cubed plus x minus 2 equals 0. Well, that is a 0 at 1. That's the other endpoint, isn't it? This one has a 0 at -1. This one has a 0 at 1. Can we factor it? Yeah, we'd say x minus 1 is a factor. The other factor will have to be x squared. What? So we got a negative x squared here, so we need a 2x squared to, oh, wait. Is that true? So
Can't you just do synthetic division with that?
Yeah. I'm sorry, what?
Can't you just do synthetic division to find that?
Oh, to find what? The 1?
The other expression?
Yes. I find synthetic division to be a little bit of overkill here, but you know, it works. Let me see if we don't have an eraser here, right? Can I just wipe that out? There. So that should be an X there, right? How about that? This one, you know, you're dealing with a computer noob. And they edit their computer documents with whiteout, which the whole computer monitor is covered with. Okay, how are we doing here? So this is an X, right? Because we have these, we want these to cancel. There's no X squared term here, right? So I'm just guessing and checking. So the question was, you know, why not use synthetic division? And yeah, that would work. But you know, this is a simple enough case. I screwed it up, right? Do you want to look at the synthetic division? So you'd say we have the coefficients are 1, 0, 1, -2, 1, 0, 1, -2, and we're looking at dividing by 1, and so we bring down the 1, and 1 times 1 is 1, 1, 1, 1, 2, 2, 0, right? So it's a 0. Does that look familiar to you folks? You know, if you're taking pre-calculus last summer or recently, you would have done that. Okay. And so that means that the next number here is a +2, huh? Yeah, that'll work. I'm going to write +2 equals 0. Does this factor? Well, what's the discriminant here? It's 1 minus 8, right? B squared minus 4AC is going to be 1 minus 8. So this is irreducible. Doesn't have real zeros. So we don't have to worry about that one, right? It's irreducible over the reals, right? So, well, that's great, except now we do have trouble spots, right? What happens if we add these things together? Can we get a common denominator and multiply them together? Let's try that. F of x equals a times x cubed plus x minus 2 plus b times x cubed plus 2b x squared. Oh, sorry, plus 2x squared minus 1 all over. The common denominator is going to be the product of these two things. And this one, when you factor it, has a factor of x plus 1. This one has a factor of x minus 1. When you multiply those together, you get a factor of x squared minus 1, just difference of squares. Oh, sorry. Yeah, that's visible. And the other factors are this one, which has 2 real zeros, one of which is on the interior of the interval, so that's a worry. And this one, which has no real zeros. Do you want to combine like terms, expand and combine like terms in the numerator? What do we get? We'll get a plus b times x cubed. We're going to have 2bx squared. We're going to have a plus ax and minus 2b minus o. That's a 2a minus b all over x squared minus 1, x squared plus x minus 1. Okay, so we want some subinterval. We seek a subinterval.
What is a subinterval?
That's an interval contained in our interval. So our interval is -1 to 1, where that is, i.e., A, B contained in like a subinterval, a subset of -1 to 1. Is that set notation okay? This says subinterval or subset, right? And since these are intervals, it's a subinterval, right? Yeah, thanks for that question. I see that Kenny must have said something here. What did you say? That I have a response to you? I'm not sure. There's a lot of discussion here, which I think I missed some. Okay. Can you extend the due date for 2.5 was his question. Sure. Yeah, remind me to do that. Okay, so, and that was a private question, so maybe I shouldn't have said who asked it. Never mind, I can't help myself sometimes. So such that, I'll write out the words, how's that? F of A times F of B is less than 0. Why? Well, that's sort of an elegant way of saying that F of A and F of B have opposite signs, right? If one is positive and the other is negative, then their product is negative, right? Oh, I should have used some other characters, right? I'm using A and B for the numerators. Oh, no. Here's CD. Such that F of C times F of D is negative, right? In that case, that, you know, since, oh, and our function is continuous on CD, or yeah, CD, the closed interval, right? So F of C and F of D have opposite signs, and the function is continuous on that subinterval. So I think we should probably bring out some big guns to examine what's going on here. And the big guns we have is GeoGebra, right? So let's go ahead and you don't really need that, do we? So I'm going to actually make two functions here. I'm going to say g of x is equal to a divided by, what is it, x cubed plus 2x squared minus 1. Oh, create a slider for a. Yeah, if you don't provide one, it will provide one for you, right? And notice that this is including negative values of a, so I should edit that. It's very confusing because I have now 3 mouse pointers on my screen. One for my OBS, which I suppose, yeah, I kind of need that. One for the Zoom and one for the actual application. All right, so I want to edit the properties. And I think, you know, let's say between 0 and 5, okay? All right. And, oh, we're kind of zoomed in here, aren't we? I don't know why I'm so zoomed in. Oh, can I just go to Window, Tools? Yeah, I guess I don't have that tool here, right? The sort of give me a standard zoom tool. That was later versions of GeoGebra got that, so I must have been zooming in for some reason, but here we are, okay. Okay, so this function is 0, right? Because a is 0, so if I give it a little value here, we can see, you see the vertical asymptote? Okay, so we do want to zoom in on the horizontal here, right? Hello, horizontal. Okay. All right, so we're between -1 and 1. where we want to focus our attention here. And we see, there's a vertical line. Should we draw that? I mean, because we know what it is, right? It's x equals -1 plus √5/2, right? So I'm going to say, yeah, the line x equals -1 plus square root of 5 all over 2. Illegal division. Oh, I got an equal sign there instead of a plus sign, right? So there's that line, and I should make it like a dashed line, right? Can I make it a dashed line? So I don't know, where do I, object properties, style, how about like that, okay. All right, so it doesn't matter what the value of A is, it has that same vertical asymptote, right? Except if A is 0, obviously things are bad, right? But yeah, so we've got this problem. And this does not have any intercepts on the interval, right? So we're going to need that second function. So let's say h of x is the function b, and it's going to ask me for a slider for b. All right. B divided by x cubed plus x minus 2. Is that a cube there? X cubed, all right, plus x minus 2. Create a slider for b, yeah. Edit that slider, yeah. We don't want it to go negative, right? Okay. So now this function doesn't have any vertical asymptotes on the interior. I guess I should also mention this one has a vertical asymptote at -1, right? So should we also draw that? So x equals -1. Remember, that was also a vertical asymptote. And can I, properties of that, and also make it dashed. Okay. And then this one has a vertical asymptote at +1. So let's draw that in. X equals 1. And I guess enter. And so we want that to be dashed as well. Okay, so there are 3 vertical asymptotes at this stage for the 2 functions. Now, when we add the functions together, does that preserve the vertical asymptotes? That's a good question. Not necessarily, maybe, huh? Let's find out. So I'm going to take a new function. F of x is the sum of g of x and h of x. Now, is that a dashed function? Why is it dashed? Maybe just because that's the last thing I had on here, right? And do we want to make it a color? Let's make it black. I guess black is good. And yeah, we see that, yeah, there is an intercept here, right? But it's, and notice that that intercept is less than, so let's turn these guys off, right? G and H. We're just interested in their sum now, right? Yeah, so where is that intercept? Can I plot it and then ask it where it is? Where are you? I'm at about 0.80191. Okay, what happens is I move these, oh, well, it changes, right? It moves around. Does it always exist? Looks like it, right? Now, it looks like it's always, oh, yeah, look what happens when I take b equals 0. Well, then that second function goes away. But yeah, it looks like it's always less than that vertical asymptote at about 0.72. Oh, sorry, there was a vertical asymptote at 0.72. What happened to that? Is that our g of x? Oh, did I turn that off, or did it just not come up? I thought I had plotted that, but now I don't see it, right? There's only the -1 and 1. What happened to that third vertical? I must have deleted it somehow. I don't remember doing that. How are you doing? This is, okay. Yeah, right. So we have stated what the intermediate algebras. Sort of reading the chat here. Yeah. So we're using the intermediate value theorem, but we want to find some interval of the given interval on which we can apply the intermediate value theorem, because this function is not continuous on the given interval, right? So you've got to find some subinterval. And let's go ahead and draw that other. I don't know what happened. X equals, what was it, -1 plus square root of 5. All over, 50, all over 2. Okay. And so there's that. Oh, I had it about 0.7 something. I must have made a mistake. Yeah, in fact, of course, that's 0.618. That's a very familiar number. I don't know why I thought it was 0.7 something. I'm doing that in my head. But yeah, this is the golden ratio. Anybody? Yeah. Famous number. We can talk about why it's called that at some later time. But let's go to style, make it dashed, and say, yeah, notice that our solution, and that's what the point of this whole GeoGebra thing is, that no matter where we put A and B, our solution is always in this interval between the golden ratio and 1, right? So that's where we want to create our subinterval. And we can't take the golden ratio as, so let's turn off G here. Right, we can't take the golden ratio as one endpoint because it's not continuous there, right? It's a vertical asymptote. We can't take 1 as one endpoint because it's not continuous there. And notice what happens when we take B small. It seems to get arbitrarily close. As B gets arbitrarily small, this thing gets arbitrarily close to 1 there, right? Yeah, very close to 1. And of course, it disappears when B is 0, but we're not allowed to take B equals 0, right? B has got to be some positive number. So what does that suggest about our interval? Yeah, if I take A small enough, then it gets arbitrarily close to that one. So I've got to say, I've got to use an epsilon, right? So I'm not going to finish this, but and maybe we'll finish it next time because we're sort of short on time. But let me say what we've got to do based on what we just discovered, right? And that is observation shows, right? That if I'm going to say epsilon is some positive number, should I say it's less than something? Yeah, here's how you say this. You say epsilon is positive, but smaller than 1. Much smaller than 1, that's what that's saying. This is not standard notation you'll read in the book, but that double less than sign, I learned that in school. That means much less than, right? So epsilon is positive but small. That's what that's saying, right? So if epsilon is a positive but small number, then f of x is continuous on f of oh, sorry, not f of, but on the interval from -1 plus root 5 over 2 plus epsilon up to and including 1 minus epsilon. All right, so that's the interval we'd have to choose. All right, that's an interval where it's continuous and it's going to contain our solution. That's what we observed on GeoGebra, right? And so all we have to do is show that if we make epsilon small enough, I think it doesn't have to be very small, that f of this number will be positive and f of that number is negative, right? So we will show that 0 is between this number, where it's negative, and this number. So this is the subinterval we seek. This is C and that's D, right? -1 plus root 5 over 2 plus. So yeah, that's a tricky problem, no doubt. Can you read that at the bottom there? Okay, I've reached the end of my sheet, so that means I'm done. And so how would we actually establish this? I mean, we kind of established it by looking at GeoGebra. Is that satisfying though? I think it seems like a little bit cheating, but we're going to move on anyway. Any questions about that before? Did I previously go over the intermediate value theorem? Yeah, that's the big theorem at the end of section 5. It says that if f is continuous on a closed interval and you have a number n between f of the left endpoint and f of the right endpoint, then there's some number on the interior of that interval. Yeah, we did talk about it right at the beginning. So, okay, let's move on. So moving on will mean here going to the book. And in the book, we'll be going to the next section. Can I get there this way? Limits at infinity. And we've got horizontal asymptotes. Okay. So we've talked about what the limit as x goes to a of f of x equals L, right? What that means. We now want to talk about the limit as x goes to infinity or x goes to negative infinity, or I think we also want to talk about vertical asymptotes, right? So the first part is going to be horizontal asymptotes. So yeah, so you would have learned in pre-calculus the rule here, right? Which is that if you have a rational function like this one, and the degree of the numerator equals the degree of the denominator, then I don't know, can I try to scribble on here? So this is equal to 1 minus 1 over x squared all over 1 plus 1 minus x squared, 1 over x squared. So as x goes to infinity, this is going to go to 1 over 1, right? Because those, so this is as x goes to infinity, right? Or at negative infinity for that matter, right? So on both the left and the diagram shows what's happening, right? It's kind of an elegant little curve there. It dips down to -1 at 0, which looks like it's not quite the absolute minimum. It looks like maybe if you go a little bit farther to the right, it's hard to say, huh? Well, that's the kind of thing we'll be examining soon enough. Right, so what I did here was divide the numerator and denominator by -1, by x squared, right? And so I got leading coefficients in front. You can always do that if the degree of the numerator is the same as the degree of the denominator. You can divide by the x to whatever power that is, here x squared, and your remaining terms will all have x in the denominator, and they'll all go to 0 as x goes to infinity. Okay, let me see if I can I erase that? Yeah. And can we move on? Oh, no. I think I have to choose a different. I just use my mouse for crime's sake. Oh, I have to grab that and add that, and then I can go over here. Okay. So evaluating limits at infinity. Oh, I've got some more stuff I need to erase here, huh? Most of the limit laws that were given in section 3 also hold for limits at infinity. It can be proved that the limit laws listed in section 2.3, with the exceptions of laws 10 and 11, which I suppose we could look to see what those are also valid if x goes to a is replaced by x goes to infinity or negative infinity. Okay, so the limit of a sum is the sum of the limits, and so on. If r is a rational number, then if it's positive, this goes to 0. If it's a rational number such that x to the r is defined for all x, then it goes to, as x goes to infinity here, and as x goes to negative infinity there, right? So here's one where, it's the degree, it's a rational function, the degree of the numerator equals the degree of the denominator, and they're doing just what I demonstrated before. Here's another one where it's not a rational function because that's a root function on the top, but yeah, they're sort of working it all out for you here, right? Oh, why is it blue? Okay. So what do? We divide the numerator and denominator by x, yx. Well, you can factor out the square root of x squared on the top, right? Or you could bring in, so x, as x is going to infinity, it's positive, right? So we can replace,
Professor, would we ever be allowed to use the fact that we can use leading coefficients and things like that, like looking at the 2x squared and comparing that to the 3x, but the fact that the square root's there, we can cancel out the squared from the 2x squared?
Yeah, not
and we
only
just
can
get
you use them, but you need to develop the intuition about them, right?
Yeah, just to make it a lot easier instead of doing all that work there.
Well, you need to be able to do the work too. I mean, so the work is more formal.
Yeah.
How do you, formally justify this? But, don't just do the formal thing, right? Because then you're not really thinking. You're just, oh, when I see this, I do that. You want to develop that intuition about how does the numerator behave here. As x gets large, the numerator behaves like square root of 2x, right?
Yeah.
The plus one doesn't matter. If x is very large, like 1,000,000, then the square of 1,000,000 is what? Trillion. So, that 2 trillion plus 1, for all intents and purposes, is 2 trillion, right? If you give a 2 trillionaire $1, they're going to get down on their knees and thank you for that because now they'll be able to have a cup of coffee? No. Okay. But yeah, this is so I mean, that's a fair question, right? So do you have to do all this just to, to show that this is square root of 2/3 as the leading coefficients, right? Well, it's not quite, because that's not quite a polynomial. It's a square root of a polynomial on the top, right? So that rule about rational functions is not strictly applicable here, although it does sort of generalize to this, right? You can see that, yeah, that does work. So what is he talking about here? Yeah, so here's another way of kind of looking at this. Yeah. Oh, so as x goes to negative infinity, you can't replace x by this positive square root of x squared, because that's the absolute value of x. And if x is going to negative infinity, then it's more like the negation of the absolute value of x, right? So that's why that negative sign pops in there. So if you wanted to apply that in this case, you would, Yeah, it's the same thing, isn't it? I don't know quite what's different about that. Oh, so yeah, I'm sorry. Yeah, of course, we're going to negative infinity, right? So on the top, when you pull out, actually, they're not pulling out the square root of x squared. They're bringing in this. So that would be another way of doing this, right? Would be to, rather than doing it that way, you could, if this is possible here, say square root of 2x squared plus 1. I can say that's equal to the square root of, hello, it's not behaving properly. I tried to put a piece of paper in there to make it a little bit more solid, but that apparently was not working. Square root of x squared times the square root of 1 plus 1 over the square root, x squared, right? Where this extends over the whole thing, right? But that's not correct if we're going to negative. Well, yeah, I mean, that's correct. Well, no, it's not, because if we're going to negative infinity and we pull out the square root of x squared, we'd want to take the negative square root of x squared. And they do that by putting in the negative here. And so this is negative x, negative absolute value of x, right, times the square root of 1 plus 1 over x squared, right? So that's an absolute value there. Sorry, it's a little hard to read, but so then as x goes to negative infinity, that's going to go to a negative. And so you end up with, and notice what the graph looks like here, right? That there are two horizontal asymptotes. There's a different horizontal asymptote as you go to positive infinity than if you go to negative infinity, right? So there's no rational function that will do that, right? So this is because it's a root function, we get that behavior. Here's another example. So here, notice that, so this is an example of where you have to be careful. And this is, one of the things you can't say, that negative infinity minus infinity equals 0, right? It's very tempting to say that, but in fact, not necessarily, right? It depends. Did I spell? I can't even spell when I write on this thing. So negative infinity minus infinity is not necessarily 0. So if you split this up as the limit of the difference is the difference of the limits, you end up with an indeterminate form. So maybe we better write that out on paper, right? So we can see it clearly. And so when you do, well, maybe we'll wait till the exercises, all right? Because I'm sure there will be some like that in there. So do you see what they're doing here? Here. They're multiplying by 1. So it's that conjuring trick of multiplying by the conjugate. Magically, we get a difference of squares, which then we're able to cancel a factor, or we're able to cancel that x squared term on the top. And so on the top, we just get 1. And okay.
In that example, did they change the x to a z?
Where?
In the conjugate?
I don't see a z. Am I missing something?
Well, maybe it's blurry here. It's a little hard to see, but it looks.
Oh, yeah. Yeah, x, I've had that problem. When x gets blurry, it's hard to tell the difference between an x and a z. I mean, yeah. Notice that how similar the shapes are in a way, right? You got a bar kind of on the top of the script x. Yeah, that's an x.
But okay, yeah. The addition.
I'm sorry if it's blurry. That's probably two things. One is, you may be viewing it on a smaller medium, and the zoom connection sometimes. I mean, on my screen it's very clear, but then I'm broadcasting, right? And so the broadcast signal is degraded somewhat, I'm afraid. Yeah. So that's if you're computing the difference. If you're going to infinity, so now then this limit as x goes to infinity grows without bound, right? And so that's going to be 1 over infinity. I tend to think of 1 over infinity as actually kind of a useful expression, right? So 1 over infinity, is that a meaningful expression? Yeah, that's always interpretable as 0, right? And I will use that notation sometimes. It's kind of frowned upon in the ivory towers, but to me it makes sense, right? 1 over infinity is 0. However, you know, this does not make sense, right? Infinity divided by itself, that's not equal to 1. I mean, it could be, depends on how you get there, right? You can't interpret this. This is what's called indeterminate. 1 over infinity is, you know, a sensible expression. Infinity over infinity is not. Okay. So what else do we got here? I suppose I could go use the, yeah. So limits at infinity. So this notation says that as x increases without bound, f of x increases without bound. And that's often the case for, you know, polynomial functions or whatnot. In fact, that's their first example here, right? Let's see, how do I, okay, pull this down. Yeah, so this increases without bound and decreases without bound as you go to negative infinity, right? Yeah, and that's you know, that's the end behavior of a polynomial, right? That's something you study in. How about this example? Anything going on here? Yeah, here you cannot say this. You know, the limit of the difference is the difference of the limits, because infinity minus infinity is not 0, right? Do we already write that? Let's see, I think I can get the, yeah, infinity minus infinity. You cannot interpret, sorry, you cannot interpret that as 0. Man, that's hard to write. Right, so this is another indeterminate form. Right, so what is the implication here? The implication is that we need to factor this, right? When you factor it, yeah, infinity minus infinity can't be defined. However, when you factor it, you can say the limit of the product is the product of the limits, because what? Don't do that. Stop that. Okay, I give up on the pen. Oh, it's doing it with the, it seems to want to highlight things. It becomes much too blue. Okay, I'm going to go here and say, yeah, infinity times infinity. Does that make sense? Yes, we can interpret that as infinity, right? If you multiply something by something infinitely large by something else infinitely large, you get something infinitely large. In fact, sometimes these are distinguished between Aleph 1 and Aleph 2, but that's a whole nother branch of math. Okay, I guess I need to go here and erase that and erase this. Okay. So here you can't take the limit of the quotient as the quotient of the limits, because you get infinity over infinity, right? So this is, we already talked about this indeterminate form. Infinity divided by, divided by infinity. That looks like a man with his nose over the ledge. You cannot interpret this as 1, right? I think we already said that, right? That's infinity over infinity. You can't interpret that as 1. However, what can we say? If I multiply the numerator and denominator by 1 over x, then I get, you know, this expression here. Why is it blue? I don't want it to be blue. Okay. So now the denominator is going to a fixed value of 1, or -1, sorry, while the numerator is going to infinity. And we can say that infinity divided by -1 is negative infinity, right? That does make sense. Okay. Do we have the right tool for scrolling? Another example. So they got a bunch more examples. So here's one where the limit of the product is the product of the limits. And this is going to be they're talking about intercepts. Do we care about intercepts? Not really, right? The first factor is going to positive infinity. The second factor is going to negative infinity. And the third factor is going to negative infinity. So basically, you know, you just look at the signs, right? So infinity times negative infinity times negative infinity again. What is that? That's positive infinity, right? Two negative infinities multiplied to a positive infinity. Okay, so that does make sense here. All
So
right.
for these ones, is the answer always either infinity or negative infinity?
Well, never say always, right? But yeah, oftentimes, how about that? And so, yeah, so here, this is like the end behavior of a polynomial. So yes, I can say always the end behavior of a polynomial of degree greater than 0, right? Because it's not a constant, will have end behavior either going to positive infinity or negative infinity, right? In pre-calculus, you learn the 3 cases, right? Where the leading coefficient is positive, or the 4 cases. Either the leading coefficient is positive or negative, and either the exponent is odd or even for the leading term, right? If the degree of the polynomial is odd or even. So you look at the leading coefficient, you look at the parity of the degree, is it odd or even? And from that, you can determine the end behavior, which will either be positive infinity or negative infinity. So yeah, you can say always in that case. All right, so we have some precise definitions. So basically, you want to say, if we're approaching a horizontal asymptote, then I can find a input n after which all the outputs are within some epsilon band of our limit, right? And here's where they're saying that if, oh, then that's the negative one. So where is this stated here? Yeah. So they have a little animation for that. I will invite you to look at that. So for the negative limit, you basically are on the other side and saying that, you know, there's some bound where if x is below that bound, then we can be sure that f of x is within epsilon of the limiting value L. And here's an example of doing that, which I'm thinking maybe we should get to the exercises so we can, rather than, you know, I invite you to read these, but infinite limit as infinity, right? So that means as x, there's some cutoff beyond which f of x can be, if x is larger than that boundary, that positive number n is what they're calling it, then f of x is greater than any. So given any number m, we can find a number n so that if the input is greater than n, the output is greater than m. All right, moving on. Exercises at last. I thought we'd never get there. So 2.6, it's 636. That's a lot of sixes all in one statement. Explain in your own words the meaning of the following. So this says that we can find n large enough so that if x is greater than n, f of x is within epsilon of 5. Is that what they're going to say here? Well, this is the more intuitive definition, right? As x becomes large, f of x approaches 5. That's not very precise, but it's intuitive enough. For the following, whose functions state the following: what is the limit as x approaches infinity? And you can't really tell from the graph, can you? Right? As x approaches infinity, you don't see what happens out here. It could be anything happens out here. So you have to kind of extrapolate from what's happening before. And it looks like x is approaching f of x is approaching -2. I got to say, it's not very convincing. So let's just move on. How about this one? As x approaches infinity, yeah, it looks like it's kind of oscillating around 2, right? That's the trend that's been established here, right? And so it's reasonable to extrapolate from that trend that the limit as x goes to infinity of g of x will be 2. And on the other side, it looks like it's approaching 1 from below. And so the limit as x approaches -infinity of g of x will be -1. As x approaches 0, either from the left or the right, looks like we're diving down to -infinity. So this one would be c would be -infinity. As you approach 2 from the left, you're going to -infinity, but as you approach 2 from the right, you're going to positive infinity, right? So the equations of the asymptotes are x equals 0 and x equals 2, right? Oh, and I guess y equals 2 and y equals -1 are the horizontal asymptotes. Oh, 5 through 10, sketch a graph of an example of the function that satisfies all the givens. Well, let's do 10 then, right? And I'll do that on pencil and paper. So here, what are the givens? So this is 2.6, number 10. And we want f of 0 to be 0. We want the limit as x approaches 1 from below to be infinity. We want the limit as x approaches 1 from above to be positive infinity. I believe I've got that. Also positive infinity. Oh, wait. Yeah, no, this is positive infinity. Oh, negative infinity. Sorry. I have to be careful I read the right problem. Oh, I'm reading the wrong one, aren't I? Sorry, let's just turn this upside down. I was reading the wrong one, and I knew I had to be careful. So number 10, right? This is here the limit as x approaches -infinity of f of x is equal to -1. Also, they want the limit as x approaches 0 from below of f of x is positive infinity. They also want the limit as x approaches 0 from above to be, read the right problem now. This is -infinity. Can I fit that in here? Okay, just barely, huh? And number 10. Okay, so I've got the first three, and that there's 4 more. Okay, so the limit as x approaches 3 from below of f of x is 1.
Why are you saying above and below? Is it not left and right?
Yeah.
The same thing, right?
Yeah, I think of less than as below and greater than as above. But if you're literally thinking like above is higher, which means vertical, then you're right. I should say for the left and right. Okay, I'll try to be more careful about that. But yeah, I mean, that's what I meant. So I should say what I mean. Okay, so this is 1. And we also want that f of 3 to be 4. And f of the limit as x approaches 3 from above sorry, from the right, thank you, of f of x equals 4. And finally, the limit as x goes to infinity. And this we won't be able to actually show. We'll just have to show a trend that suggests that, right, of f of x, because we can't go to infinity. We're finite mortal beings. Infinity is beyond our mortal grasp. We do the best we can. We have the calculus, right? Okay, so let's try to satisfy all these things. So as x goes to negative infinity, well, let's get the lay of the land, right? So we've got output values 1 and 4, and so those are mostly positive, but we also are approaching -1. So I'm going to make a graph here that emphasizes where the action is, right? And so that's going to be kind of like this, and we have input values 3, and that's it, right? That's the only input value we have. So let's make our axis a little bit here. So 1, 2, 3, 4, and 1, 2, 3, perfectly evenly. Well, I do my best. So the horizontal line, -1, is going to look like this, right? Make a little dashed line. This is an asymptote, a horizontal asymptote, right? And we really only care about what happens on the left side, right? So I'm going to write that in. The limit as x approaches 0 from the left, it's going to positive infinity. So I'm going to draw, and I think that kind of covers, yeah, so I could just draw something that does this. I mean, this is sort of the simplest way of satisfying those first two requirements. Yeah, and the limit as x approaches 0 from the right is negative infinity. The limit as we approach 3 from the left is 1, although f of 3 is 4. So let's write f of 3 is 4 here and put an open circle here. And I'm just going to, it doesn't say where the intercept is, so I'll just, not pay attention to that really, right? But this is then grasping those things. And we have two more things. Oh, really? So as we approach 3 from the right, we're equal to 4, and we're going to drop down to 1, right? And so I'm going to sort of indicate that by actually drawing the asymptote as a dotted line. That really is evocative of the notion that we're approaching 1, right? Okay. So that's just sort of interpreting the notation in terms of a graph, which is a good thing to do. So let's, any questions about that, or it's pretty straightforward, I think. Okay, so how about 14 here? What's going on? Can we take the limit inside the root? Sure. If we do, what do we have? Inside the root, we have a rational function. Why can we take the limit inside the root? Well, that was one of the early limit rules. As long as the thing inside the root is positive, we can take the limit inside the root. Okay, and inside the root, we have a rational function where the degree of the numerator is 3 and the degree of the denominator is also 3, right? No. Well, that means we can just take the ratio of leading coefficients, right? So that's going to be 9 under the radicals, and the radical of 9 is 3. So find the limit. This is in 15 through 42. That's a lot of problems. Find the limit or show that it does not exist. Okay, well, obviously we don't have time to do all of these. This one is a rational function, degree 4 over degree 4, so just ratio of leading coefficients, right? And it doesn't matter whether you're going to the left or the right then, right? This one is that trickier one, right? Where we're taking the positive square root. So if you're going to positive infinity, you don't really have that point of confusion. But if you're going to negative infinity, like say this one, right? What's going on with this one? Shall we write that one out? Let's do number 26. Get my mouse over here. So this is 2.6, number 26. Oh, look at that. And we have the limit as x goes to negative infinity of positive square root of 1 plus 4x to the 6th divided by 2 minus x cubed. That's a cube there. It looks like a blob. But yeah, so the numerator goes like 2x cubed, right? As x gets large, that plus 1 doesn't matter, right? Or it's inconsequential. And the denominator goes like negative x cubed, right? And as x goes to negative infinity, negative x cubed goes to positive infinity. The numerator goes to also to positive infinity, right? So this is infinity over infinity. Oh, wait, you can't do infinity over infinity. That doesn't have a reasonable interpretation, right? So what do we do instead? Here I'm going to, I'm going to do it a little bit differently than the book did it, right? The book says, I forget what the book said. So I'm going to say, I can take out the square root of x to the 6th. Let's say 2x to the 6th, right? And the square root of, the square root of 4x to the 6th is 2x cubed. So I'm going to leave a little gap there because I'm not sure. Do I need to put a negative sign here? And so now this is 1/4. Oh, sorry. 1 over 4x to the 6th, right? Plus 1. Now I'm going to negative infinity, so this should be a positive number, right? Because the numerator is a positive number, right? No matter what we put in here, when we take the positive square root, we're going to be taking the positive square root of a positive number. But as x goes to negative infinity, this cube is going to be negative. So I have to put a negative there. All right, so that now as x goes to negative infinity will be positive. So it preserves the positivity, right? And what do we have on the bottom? Well, on the bottom, I'm going to write negative x cubed plus 2, just sort of emphasize the leading term is x cubed. So there you can see we got negative 2x cubed over negative x cubed. That kind of looks like it's going to go to 2, doesn't it? How can we make that more precise? I suppose we could divide the top and the bottom by negative x cubed, right? If we do that, then we'll have the limit as x goes to negative infinity of 2 on the top, square root of whatever that is, right? 1 over 4x cubed, x to the 6th, plus 1. And on the bottom, we'll have 1 minus 2 over x cubed, right? We divided the top and the bottom by negative x cubed. So now this term goes to 0, right? And this term goes to 0. So you're going to have 2 times the square root of 1, which is just 2 over 1. That's 2. There are other good arguments you could make. You can make one more like the book makes. I think they take a slightly different approach. But yeah.
Could you explain what you did to with the original one to get to the negative 2x to the 3rd and then get the 4x to the 6th in a fraction?
Yeah. So part of what I did was say 1 plus 4x to the 6th, that's equal to 4x to the 6th times 1 over 4x to the 6th, right? Plus 1. Would you agree that's true?
Right.
Right. So that's what I have left under the radical here, right? So if I take the positive square root of this, then I'm going to have the positive square root of that, right?
Right.
And so now the positive square root of 2x to the 6th is technically 2 times the absolute value of x cubed, That would be another way of doing this, right? Why the absolute value? Well, that comes from the fact that the square root of x squared is the absolute value of x, right? Is that well known? Why? Well, because if x is negative, then I'm going to square it and take the positive square root. That's not x, that's the opposite of x, right? So how about an example? The positive square root of -2 squared. Well, that's the positive square root of 4, which is 2, not -2, right? So if I were to write x here, that would be wrong. But yeah, the absolute value of a negative number is the negation of that number. All right, so the absolute value of x cubed, well, if x is negative, then x cubed is negative, right? But I want a positive number here. So I take the negation. I mean, this is the point of confusion often, right? Is negative x cubed negative? Well, yeah, it's got a negative there. It must be negative. Well, no, if x is negative, then x cubed is negative, and the negation of a negative is positive. But I want, yeah, so if I didn't have the negative, I'd have a negative. If I didn't have the negative sign here, and x is negative, then x cubed would be negative, but I want whatever is here to be positive. Does that help? Oh, your laptop had an update out of nowhere? Yeah, that's Windows 10 for you. It'll just say, oh yeah, it's time for you to have an update, and then it takes all day because it totally rebuilds the operating system. At least that hasn't happened to me in a while, but it did happen a couple of times. That's pretty annoying. Okay, so that's number 26. Did we finish it? Yeah, we got 2, right? Okay, so what other goodies do we have here? Find each of the following. So we got 2 over x. As x goes to infinity, that'll go to 0. And natural log x goes to infinity. So this would go to 0. And 0 minus 0 is 0. That's fine, right? But yeah, so let's do number 44 because I think this deserves some attention. Okay. Because you're going to have some indeterminate forms here. So this is number 44, 2.6, number 44. So f of x is the function 2 over x minus 1 over natural log x, right? And find each of the following limits. So this one is easy, right? The limit as x goes to negative infinity. Oh, to positive infinity. The domain of x, I mean, the domain of natural log x doesn't admit negative or 0, right? So we couldn't go to negative infinity. That would be outside the domain. So it would not exist for that reason, I guess, right? This is just, you know, can I use the shorthand? So here's my interpretation of this. I don't know, if you wanted to include another step, you might say the natural log of infinity. What's that? Well, that's infinity, right? Natural log increases without bound. You just imagine the curve of the natural log of x. It rises slowly, but eventually it can get as large as you like, right? You know, the natural log of e to the billion is a billion. The natural log of e to the trillion is a trillion, right? So by making the input e to whatever power, you get as large as you like, right? So this goes to 0, and that goes to 0, and so the whole thing is just 0, right? That's a good enough explanation for me, right? Okay, so how about so this was part 1. There's a part 2 where we see the natural log of x as x goes to 0 from above. That's a little bit trickier, right? So here's our function, right? So that's going to be 2 over positive 0. Yeah. So can we do this? Well, let me put a little question mark here because I don't know if this is going to work, right? But as x approaches 0 from the right, I should say, right? Then we get 2 over positive. That's my shorthand for I'm approaching 0 through positive numbers. And I can do the same thing here, right? Natural log of 0, a small positive number, right? And so how would you interpret these? Well, this would be positive infinity, and this would be 1 over the reciprocal, 1 over negative infinity. Does that works, doesn't it? Right. Yeah, again, imagine do you have in your mind's eye a picture? Well, let's put it in our real eye. Right. So here's the graph of the natural logarithm. Right. It's got an intercept of 1 and it goes to infinity. Right. So it rises without bound. It rises very slowly, so it may not appear that it's rising without bound, but this is y equals natural log x, and so it's diving down to negative infinity as you approach 0 from the right. And so is this something we can interpret, intuitively? I would say, yeah, this is infinity minus 0, right? So this is infinity minus 0. 1 over negative infinity, well, that's going to 0, right? And infinity minus a constant or infinity plus a constant, that's just infinity, right? So that's the best. I mean, you can also say does not exist here, and you'd be technically correct. But the better answer is that it's decreasing without bound, right? Okay, number 3, we have any more tricky ones here? Approaching 1 from the left, yeah. The limit as we're approaching 1 from the left of 2 over x minus natural log, the reciprocal of natural log of x. What do we have here? Well, as we approach 1 from the left, we're approaching negative infinity. So, I mean, I think we can just say this is 2 over 1. If you like, from the left, that's just 1, right? So this is just the number 2. 1 over the natural log of something slightly less than 1. Well, that's approaching 0 through negative numbers. So I'm going to write this as 2. And this is 1 over negative 0. And I'll write negative 0, it's just something slightly less than 0, right? So that's that superscript dash up there. I guess that's extra textual. You won't find that notation in the text, but it works for me, right? What does that mean? That means we're dividing 1 by a very small negative number. And in fact, that's going to 0 through negative values. So I'm going to say that's 2 minus negative infinity, right? Does that make sense? Sure. That's the same as 2 plus infinity, right? And that's just infinity, right? Oh, okay, so these are not proving to be too hard. How about if as you approach 1 from the right? That's the last one of these. Limit as you approach 1 from the right of 2 over x minus 1 over natural log x. Well, that's going to be very similar, right? That's going to be 2 over positive 1. That is a number slightly larger than 1 is what I mean there. Or approaching 1 from the right. And this is 1 over, can I say just jump to positive 0, right? Just as this was negative 0, this is positive 0, which means, a number approaching 0 through positive values. So that's going to be negative infinity, right? This is 2 minus infinity. That's negative infinity. All right, questions about that? Or okay, great. I didn't allow any time for questions. We don't have time for questions. It's 7 o'clock. Oh my goodness. Okay, so that leaves us enough time to finish up chapter 2.6 exercises before a break. So, okay, use the graph of this to estimate the limit. Are we allowed to use a graph? I guess so. It's got a graphing icon next to it. And maybe we want to make sense of that. It says use a table of values to estimate, find the exact value of the limit. Okay, so if we were to just, so we're going to infinity, right? Yeah. So this thing, clearly the first radical here is going to infinity, and the second radical is going to infinity. But what do we know, right? Infinity minus infinity is not something we can interpret, right? So infinity, infinity minus infinity is not equal to 0. Actually, it might be equal to 0, but you can't say it's identically equal to 0. So sometimes to say identically, I put 3 bars and put a slash through it to say that's not, you can't say that's always 0, right? Depends on how you get there. Sometimes it is, sometimes it's not, right? We want to avoid using that. What can we do then? Well, we can multiply by the conjugate. Is that going to work here? It might, right? Yeah. In fact, let's just do that. We'll skip there. We don't need no stinking calculators. Blazing Saddles, anybody? That apparently now has a warning label on it. What a world. Yeah. Okay, where am I? Okay, we're over here. And I'm going to need a new sheet of paper for this, huh? All right. Because this is going to be kind of lengthy, and I have to write large with these Sharpies. They're not that sharp after all. So this is number 46. And here's our function. And are you getting used to this conjuring trick where we multiply by the conjugate? So this is 3x squared plus 8x plus 6 minus same leading term, right? Plus 3x plus 1, right? So I'm going to just say, multiply. If this is A and this is B, I'm going to say we're going to multiply by A plus B over A plus B. That's my shorthand for multiplying by 1 in the form of the conjugate of A minus B is A plus B, right? So what do we get in the numerator? In the numerator, we get a difference of squares, and the square of the radical is just the thing, right? So this is going to be 3x squared plus 8x plus 6 minus 3x squared plus 3 in parentheses, right? Because we're subtracting the whole thing. And then on the bottom, we get 3x squared plus 8x plus 6 plus square root of 3x squared plus 3x plus 1, right? And that plus sign makes all the difference because infinity plus infinity is infinity, right? So that's not an indeterminate quantity. But we don't want infinity on the bottom necessarily because I think the top is also going to infinity, right? So in fact, what do we have on the top? On the top, the 3x squareds drop out, right? So we get 5x plus 5, or we can say 5 times x plus 1 on the top. On the bottom, I kind of want to factor out square root of 3x squared, right? And where's our limit going to here? We're going to positive infinity, right? So we don't have to worry about the absolute value and all that stuff. I'm going to say on the bottom, I'm going to factor out the square root of 3x squared is the square root of 3 times x. And as long as x is positive, the square root of x squared is just x itself, right? Positive. Are you certain? Yes, I'm positive. Okay. So then what happens inside the radical? Well, we're going to have 1 plus 8 over 3x, all right? Because we have to divide all the terms inside the radical by 3x squared. And so we can reduce the first one by a factor of x and the second one by a factor of 3. And then that's going to be plus the square root. And I'm going to put this in parentheses, right? Because we're factoring the same thing out of each one. And that's going to be 1 plus, I think just 1 over x here. And this one is going to be 1 over 3x squared. Close parentheses.
Wait, you're dividing by 3x squared, right? Not multiplying it by it?
Right, I'm factoring out 3x squared from each radical, each radicand, and then taking the square root of that on the outside. Square root of 3x squared is square root of 3 times x, right? Or the absolute value of x technically, but x is we're going to positive infinity, right? So that's not a worry. Does that answer your question?
Yes.
Okay, so yeah, so now the limit, I guess the next thing to do is to reduce by a factor of x. So let me write this. So the limit as x goes to infinity of f of x is going to be the limit of 5 plus 1 over x on the top and square root of 3 on the bottom times, can I just write this? I don't want to write all that again, right? So what does that mean? Well, this is notation borrowed from music, where, you know, the bass player has a lead sheet, always plays the same thing over and over again, right? So rather than writing what that thing is, they just say this, right? The same thing again, right? So this one is that one, and this one is that one. I'm not going to rewrite it, right? So I divide the numerator and denominator by x, and I can see that this is going to be 5 over the square root of 3, right? Because all these guys are going to 0, so we end up with the square root of 1 here. These guys are going to 0, the square root of 1. Oh, sorry, that's the square root of 1 plus the square root of 1 is 2. Right, so I got a 2 down there, right? 1 plus 1 is 2 on a Monday. Oh, it's Wednesday. I was going to say on a Tuesday, but we don't meet on Tuesdays. Okay, are we done? Kinda. So, you know, in this problem, they wanted you to draw the graph and then do a bunch of numerical exercises and then finally find the exact value of the limit, right? And so I just cut to the chase. Here's the exact value of the limit. And if you want to do the graph, be my guest, do you want to simplify the radical? I suppose we could, right? So this is equal to 5 root 3 over 6, right? Multiplying the top and the bottom by root 3 because you don't want the radical in the basement, in the denominator. All right, so are there more problems? You betcha. We got a lot of problems. Yeah, graph these. All right, so this is sort of the same thing. Odd, even, yeah, so there's your, you know, end behavior laws. Factor first, yeah. Factor, so yeah, product. Use the squeeze theorem to evaluate this. So yeah, so here you're going to say sine x is between -1 and 1. Can I write this here? I hesitate to write here, but so you're going to use the fact that I don't know why it moves around like it's just wandering around. Stop wandering around. Seems to have lost its mind here. Maybe it's old. Yeah. Yeah, that's just weird behavior. Yeah, it's just plain old not working. I suppose, oh, so now it's wandering around, all right. Can I even erase? Yeah, I think maybe I need to get a different surface. This one just isn't working. It's like completely misbehaving. I get the eraser here. Will you work long enough just to help me erase this thing? I can't control it at all. It's got a mind of its own. Don't ask me why. Okay, I got that one. I got that one. There we go. And just put that thing away. And yeah, you can't write with the. Okay, so I think we got to a different problem somehow. Let's see, what's at the end here? Anything good? How large do we have to make X? So yeah, this is like the formal definition, right? So let's go ahead and answer one of those, all right? Use definition 9. How about 79? We'll do that one. And then we'll take a break. I think we're about there. Yeah, okay. I'll try to make this quick so we can get right to it. All right, so here, and I think I can do this here. Prove, so this is 2.6, number 79, huh? We want to prove the limit as x approaches infinity of e to the x equals infinity. All right, so that is for all m, there exists n such that, is it okay if I use that notation? You get used to it, right? It says for all m, no matter how large is the implication, right? There exists n large enough so that, or such that, x greater than n implies that e to the x is greater than m. Is that clear enough? Anybody have questions about that? People are laughing. Hieroglyphics, right? Yeah, so let me write out what this means. This means for all, and you will see this notation oftentimes. This means there exists, or there is, it's shorter to write. This means such that, which I'll give the abbreviation for that. And so this means if this, then that, right? That's the implication arrow. So that this premise leads to that conclusion. Okay, so we start out with what we want, and then we work back towards what we need in order to get what we want, right? So start out with e to the x greater than m. What does that mean? Well, that means that x, right? E to the x is an increasing function, right? Is that agreeable? In fact, it's very increasing, right? It's exponentially increasing. But that means if one input is larger than another input, then the output for the larger input is larger than the output for the smaller input, right? So it's well ordered, right? So if e to the x is greater than m, then x must be greater than what? I mean, it's just the definition. Well, no, I mean, that's what, so we want to get n, right? Yeah. Yeah, that's the right idea. That's where we want to go. So we want to say, what is n in terms of m, right? What is Nancy in terms of, I don't know, what's the NATO word for m? I think Nancy is n, right? M is mother? I don't know. So yeah, the NATO alphabet, anybody? Take a quick gander. Not that I'm a big fan of NATO, mind you, but
Mike.
they have their, what would you say? Oh, NATO alphabet is what I want. I just look up NATO. What'd you say?
Mike, as in Michael.
Oh, Mike, right. And so was I right about N?
November.
Oh, November. I forgot that one. So M is Mike and N is November. Yeah, nobody would ever confuse those, would they? Okay. Sorry, I was looking it up and you weren't looking at what I was looking. Okay, so we're still here, right? Basically, I want to say, e to the x equals m is equivalent to saying x equals natural log of m. I mean, that's how the natural log is defined, right? So since the exponential function is strictly increasing, I can also say this inequality is equivalent to this inequality. So choose n equal to natural log m, right? Then x greater than n implies that e to the x is greater than m, and that does it, right? That's all there is to it. I have my, where is it? It fell off the desk. It's my easy button. Unfortunately, like my calculators, I need a new battery. Okay. So we're going to take 10 here, folks. Any questions before we break? So somebody was going to remind me about 2.5. Was that it? Did I do that yet? No. So let me make sure I extend that. I think maybe I did already. Did I? Was there something else I was supposed to remember to do? All right. Okay. Well, we'll have the chat open here. I'm going to pause the recording. Okay. And so we're going to start in on 2.7, which is about the derivative, right? And this is we sort of hinted heavily at this, the whole chapter essentially, right? But now we have everything we need to compute the derivative of function at a point. And then also the next section will be about the derivative function. And so let's go here, here maybe, okay. And here, 2.7, derivatives and rates of change, right? So now that we have defined limits and have learned techniques for computing them, we revisit the problems of finding tangent lines and velocities. The special type of limit that occurs in both of these problems is called the derivative. And we shall see that it can be interpreted as a rate of change in any of the natural and social sciences or engineering. Okay. Tangents, right? So we talked about the slope of a secant line. The slope of the tangent line is computed by taking the limit to the slope of the secant line. And that looks like this, right? There's a difference quotient for, so this expression we're taking the limit of here is a secant line, and we're taking the limit as the 2 points come together. In fact, there's another way of describing this, which is f of x plus h minus f of x, or f of a plus h minus f of a over h, right? So that's a perfectly equivalent way of doing that. So they do some computations with that. Explore it, tangent zoom. Okay, figure 3 relates to, right, so this is the other form. So we had f of x minus f of a over x minus a as x approaches a. That's the slope of the tangent line at a, right? This is also the slope of the tangent line of a. Is one better than another? I don't think so. I think they're slightly different, but there's one is not simpler than another as far as I can tell. So here's an example, the reciprocal function, 3 times the reciprocal function. The trick there is just to clear out the fractions and then reduce by a factor of h. And that's kind of what always happens, right? You get an h on the top, a factor of h on the top, and a factor of h on the bottom. Those factors cancel out. So instead of having the problem of, oh, I can't interpret 0 divided by 0, that's indeterminate. Now you have something that, sensibly approaches a limit as h goes to 0. And does it make sense that it's negative? Yeah, 3 over x is, what is the shape of the curve, right? Think about it. It's a rotated hyperbola. And you know, the part, if you think about the tangent line at any point, it's always negative, right? And so in particular at 3, the slope of the tangent line is negative, negative 1/3. Okay, and there's a picture of that, right? So here at x equals 3, the function passes through the point 3,1. And we can actually find the equation of the, because once you have the slope, you have a point in the slope, you plug into the point slope formula, and you get the equation for the tangent line. Velocities. Well, so this is just a physical interpretation of that same thing. So if we have a function that gives you our position at time t, then the rate of change in position per change in time, that's defined to be the velocity. We can have an average velocity. That's like the slope of the secant line, like here, right? The average velocity. This is the slope of the secant displacement over time, right? The displacement is the change in the output. That's the change in position. The corresponding change in time is just h, right? The difference between a plus h and a is just h. And we get the slope of the tangent line, gives you the instantaneous velocity. Of course, the conundrum here is that, you know, if you're talking about an instant, then no time passes, no motion can take place. So what are you talking about? There can't be any velocity in an instant. Well, it's you know, the idealized notion, and you know, we sort of all experience velocity. We're driving through our with our car or bicycle, or maybe just walking along, right? You got a speed, you're changing position over change in time, and at any instant we can talk about what is that rate of speed. But in order to talk about it at an instant, we need the concept of a limit, right? You know, average velocity is simple enough, but the limiting value of that is the instantaneous velocity. So the velocity of a ball as it hits the ground is therefore, yeah, all right. So I'm sorry, I skipped to the end. Start at the beginning and keep going until you reach the end. Suppose a ball is dropped from the opposite, and we already saw this in the first section, right? What is the velocity of the ball after 5 seconds? So that's the instantaneous. So when they say, what is the velocity after 5 seconds, they mean when t equals 5, right? So you're going to need to, so here they take the limit of the difference quotient. Can we look at this? So the velocity at any time a is going to be the change in position over the change in time as the time, so it's limiting value of the average velocity, right? So the average velocity over h seconds from a is given by that expression. And what do? They expand the square. Notice that the a squared minus a squared cancels out. That's crucial because all the remaining terms have a factor of h. You can factor that h out, reduced by that factor of h, which is going to 0. That was causing the problem of, you know, the indeterminate expression. And then you get the instantaneous velocity. It's the magic of calculus. So derivatives, so the derivative at a point is this limiting value at that point, right? F prime of A is the notation. So why the prime? I don't know. It's just notation, right? It's what has been developed over time. There's alternate notations. What other notations do we have? Well, we'll see, right? I think they're going to introduce them. So that's the F prime of A notation. And they do some computations with that. Then they find the slope of the, if you find the slope of the tangent line at A, and you have the point, A comma F of A, right? That's a point on the curve. Then you've got a point in the slope, you plug into the point slope formula, and you have an equation for the tangent line, right? I think we've already kind of mentioned that. So this is kind of repetitious in a way, isn't it? So here's this guy talking about rates of, okay, so we have delta x. So here comes an alternate notation, right? Delta x is difference in input values. So you have two input values, x1 and x2. Delta y is the corresponding change in output values. The ratio of change in output per change in input is the slope of the secant line from x1 to x2, right? And there's another representation for that. Here's a notation, the graphical representation. Here are the 2 points on the curve, P and Q, corresponding to inputs x1 and x2. The slope of the secant line, delta y over delta x. As we take the limit as x2 goes to x1, here we see the limit of the slope of the secant line. And there's a new notation we're going to introduce. I bet you it's coming right up here. Oh, well, maybe not. Okay, I'm looking for the new notation. So there's a note on units. So note that if the output is measured in dogs and the input is measured in cats, then the rate of change of output per change in input is going to be measured in dogs per cat, right? So substitute whatever units you like, miles per hour, meters per second. You can also have meters per meter, or you can have grams per meter. How could you have meters per meter? Well, that's essentially what the radian measure is, right? It's a ratio of meters per meter, so you get a pure number. But you were kind of thinking of it as meters per meteor, right? It's the ratio of arc length to radius, right? Both of those are measured in meters. All righty. So I'll let you read over these applications to various fields, sociology and biology, and then we get to the exercises. Hooray for exercises. And let's start at number 1. Always a good place to start. And write an expression for the slope of the secant line. And I guess that other notation is going to have to wait. I mentioned there would be other notation, and we'll get that in the next section. Okay. So a curve has the equation y equals f of x. Write an expression for the slope of the secant line through the point where x is 3 and the point where x is unspecified. All right, so that's going to be, f of x minus f of 3. There are alternate notations. So let's just look at their answer since they've got it here, right? So obviously, right, the slope of the secant line. Write an expression for the slope of the tangent line. That's going to be the limit of this expression. And P is where x equals 3, right? So we're going to take the limit as x goes to 3 and get the slope of the secant line at 3. Could we also take the limit as 3 goes to x? No, 3 is fixed. 3 can't go anywhere. For some values of 3, it's smaller or larger, but no, that's silly. Okay, write an expression for the slope of the tangent line at P. There it is. Okay, so here's y equals e to the x. We're in various viewing rectangles. So when you zoom in on a smooth curve, so the moral of the story here is they're getting smaller and smaller intervals. Well, I guess different intervals. Yeah, here they're getting smaller, right? What do you notice about the curve as you zoom in towards the point 0,1? And for any smooth curve, this is true. If you zoom in close enough to a smooth curve, it looks like a straight line, right? In fact, what is that straight line? It's the tangent line. It looks like the tangent line, right? So if you're very close to a smooth curve, like the flat Earth people think we live on a flat Earth because we're very close to the surface of the Earth. And are there really flat Earth people? I always thought that was some sort of weird psyop. There aren't flat Earth people anymore. Come on, somebody's got to be paid by the government to tell you that. So find a. Oh, is this? There's not a transcript of this, is there? Oh, geez, I'm going to get in trouble. Okay, so how's the things going in the chat? I was hoping for what? You said you wanted them to be pushed to Saturday. I'm sorry, what am I pushing to Saturday? Okay. Yeah, I did publish a couple of old exams you can look at. Yeah, so we said you wanted them pushed to Saturday. I'm not sure what's going to Saturday. 2.5 homework? Oh, is that what you wanted?
Oh,
Okay,
yeah,
so-
we were talking about the homework earlier. I'm
Yeah.
having really hard time.
Would Saturday be better? Okay, yeah, I get Jonathan in particular has the weekend off, I think, and so that's a better time to work. I get it. I will. Can I do that right now while I'm thinking of it? Yes, I can.
Thank you very much.
Is that 2.5?
Yeah, I should be able to get 2.4 done by Friday, but 2.5,
Okay.
I'm just
Yeah, so let's say I'm going to schedule 2.5. Okay, I guess I have to do it this way. Edit schedule. Can I show it for Saturday? Yeah. And how about at midnight, right? Oh, PM. Okay. And I think 2.6 is due at a later time or something. That's next week, right? Okay. Fair enough. Okay, so where are we? We are in the book. So find the slope of the tangent line. Okay, so using definition 1, using equation 2, find an equation for the tangent line. So for a cubic, I guess we should do this one, right? The classic, you can't just skip it, can you? No. Okay, so so this is 2.7, number 4. And so find the equation to the tangent line to the curve y equals x cubed plus 1, right? At the point 1, 2. So that's where x equals 1, right? So I'm not sure what they mean by definition 1 and equation 2, but let me show you the two basic ways and we'll compare, right? So we can take the limit of the secant line of f of x minus f of 1 over x minus 1 as x approaches 1. And substitute for everything here. So this is x cubed plus 1 minus 2, I guess, right? Yeah, f of 1 is 2. And that's going to be over x minus 1. And this is as x approaches 1. And the limit as x approaches 1. Notice I keep writing limit because I haven't computed the limit yet. And in my memory, which is limited, but it does extend over some period, students often get lazy and just drop the limit. They just start working with the expression. That's okay as long as you don't write equals, right? So I haven't written equals here, but I could, right? Because in fact, I have a run-on expression. So I keep simplifying the expression. So on the top, I've got x cubed minus 1, right? On the bottom, I've got x minus 1, right? And difference of cubes factors, right? In fact, I could do this for higher powers as well, right? And we will do that. So x squared plus x plus 1, is that the way you factor a difference of cubes? And I'm going to put times 1, right? Because I can, and people sometimes get confused. Well, I canceled that, so there's nothing left, so I'm dividing by 0. No, you're dividing by 1, right? When you cancel. And so those cancel out. And I get, can I just plug in 1 now? Yeah, I just got a polynomial, so that's going to be 3, right? So the slope of the tangent line is 3. Let me show you the other way of doing that. We could take the limit as h goes to 0 of f of 1 plus h minus f of 1 all over h, right? Same thing. Yeah? X is 1 plus h. And so as h goes to 0, 1 plus h approaches 1, right? X approaches 1 is the same as x approaching 0. So x approaching 1 is the same as h approaching 0. So we substitute for the function. Okay, so h is going to 0. And 1 plus h cubed. Can I write that? I'm going to expand that on the fly if you don't mind. So that's 1 plus 3h plus 3h squared. Am I going to be able to fit this in here? No. So f of 1 is, yeah, maybe I can, right? That's going to be minus 2 again, right? There. I managed to squeeze that in there. Should plan ahead, right? And so this is over h. Uh-oh. This is looking bad. I want that to cancel out, right? Oh, I forgot the plus 1, right? Our function is x cubed plus 1. Here I just have 1 plus h cubed. I need to add 1 to that, right? Which is good. I didn't leave room for it, but I put it in front, okay? So now I have 2 here. 1 plus 1 is 2 on a Wednesday. And so these 2's cancel out, right? And then every other term that's left in the numerator has a factor of h. That's a joy to us. For now, we can reduce by a factor of h. I'm going to factor it out. I'm left with 3 plus 3h plus h squared, right? All over h. These guys cancel. And so what happens is h goes to 0. This goes to 3. Same result. I don't know, do you like one better than the other? And the one you have to factor. In the first one, we had to factor a difference of cubes. In the second one, we had to expand a cube. Now, so factoring is easier than use the first one. If expanding is easier, use the second one. The factoring seems to actually take less, fit better on the page, right? But yeah, on the flip side, factoring is generally harder than multiplying, so whatever. So now the equation of the tangent line is y minus f of 2 equals f prime of 2 times x minus 1, right? I'm just plugging into the point slope formula. And so we computed f prime of 1, sorry. This is 1. Yeah. We're looking at the tangent line at 1, where the output is 2, but the input is 1, right? So f of 1 is 2. So this is y minus 2 equals 3 times x minus 1. And I suppose we could solve for y, and we get y equals 3x minus 1. Yeah, negative 3 plus 2 is negative 1. And what does that look like as a curve? Well, so here's 1, negative 1. So this is an intercept here. This is an intercept there. At 1, we're at 2. Oh, this point here. So the curve kind of looks like this. And the tangent line then has an intercept of negative 1 and a slope of 3. Does that seem convincing enough? Yeah. Yeah, there's, okay. So that would be negative 1. I mean, it's in the ballpark. It's a pretty rough and ready graph. I didn't label my axes. Don't forget to label your axes. I did scale my axes, so this is 2 up here, right?
Professor, so just to clarify, f prime of 1 is going to be the answer you get from solving the limit, right?
Yeah, f prime of 1 is the slope at 1, and that's exactly what this was all about, right?
Okay.
Yeah. Right, f prime of 1. So yeah, maybe I should have written that here. Right, that's what that means. And this is also f prime of 1, right? 2 different ways of computing the same thing. All right, so let's move on. What do we got here? 9, 10, a cliff diver plunges from a height of 100 feet above the water surface. The diver falls in 2 seconds. The distance the diver falls in 2 seconds is given. Yeah, this is near the surface of the Earth, right? The acceleration due to gravity is 32 feet per second, and half of 32 is 16, so that's what goes there. All right, let's move on. A rock. This is on Mars. Okay. Particle starts moving to the right along a horizontal line. So this is sort of rectilinear motion. The graph of the position is shown in the figure. Oh, this is meters and seconds. When is the particle moving to the right? When is it moving to the left? When is it standing still? Well, if the position is increasing with time, then it's moving to the right. If the position is not changing, then it's sitting still. Now, this is an abrupt change in velocity here, right? So it's like it was moving at a constant speed, and then it slammed into a wall and abruptly stopped, right? And then after it recovered its senses, it started moving backwards at the same rate that it was moving forward. But guess what? There was a wall where there wasn't a wall before, and now it's slammed into that wall. And so it's dizzy and sitting still for another second here. And then it moves off towards the other wall at a slower speed. I don't know, whatever. The graphs of the position function of two runners, A and B, who run a 100-meter race and finish in a tie, right? They finish at the same place. So this is like the rabbit and the hare, maybe. No, the rabbit like takes a nap, right? So it would be sitting still for a while. So this runner A runs at a constant speed. Runner B starts out slow, but then gets faster and faster. I'm just going to leave it at that. For the function g, whose graph is shown, arrange the following numbers in increasing order and explain your reasoning. So g prime of -2, that's back over here, that's positive. G prime of 0 is negative, so we're going down to the right. G prime of 2 is going up, but not as steep as at -2, right? So I'd say G prime of 2 is bigger than G prime of 0, but less than G prime of -2. And G prime of 4 is also bigger than G prime of 0, but I think it's tapering off, right? So the G prime of 4 would also be less than G prime of 2, which I think is less than G prime of -2, which is, they're all greater than G prime of 0. Just talk that through. I'm not going to write anything. So for the square root, guess what you're going to do? You're going to do your conjuring trick with the conjugate, right? For a fourth power, you can still factor a difference of fourth powers the same way you factor, I mean, very similar way you factor. So let's jump to 22. Maybe that would be a little bit more challenging, huh? And it doesn't have an answer given there, so I'll work that one out. Number 22. Coming up on 8 o'clock, I'd like to sort of transition to the next section, because I think it won't take long to sort of talk that one through. But 22, so we want f prime. So here's our function, right? So one that's a reciprocal of the square root of 2 more than twice the input. So we want f prime of 1 here. And that's going to be, I guess, the limit. Let's say as x approaches 1 of f of x minus f of 1 over x. Same basic thing that we did in the last one, right? But now it's a different formula. So let's substitute. And we're going to get this is 2x plus 2. And f of 1 is going to be 1/2. And this is over x minus 1. So what do we do here? Can we just plug in x equals 1? Well, no, of course not. That's going to give us 0 over 0. I'm kind of used to that, right? So we could clear out the fractions. Would that help? I think it would, right? Part of the problem here is that we got sort of a what's it called, a complex fraction, a fraction of fractions. So what would you multiply by? Well, you know, the least common multiple of these two denominators, right? So I'm going to multiply by 2 times the square root of 2x plus 2 divided by itself, right? And what happens when I do that? I'm going to get the limit as x approaches 1 of here, I'm just going to get 2, right? And there I'm going to get minus the square root of 2x plus 2. And on the bottom, I'm going to get all of that, right? So don't bother multiplying it out. Just leave it like this. Multiplying it out is actually a bad step here. I think, maybe not. If experience is any guide, actually. And you couldn't multiply that anyway, right? Yeah. Because you got a radical there, right? So now what? Well, now I'm going to multiply, but I still can't plug in 2, right? If I plug in 2, I've got 0 over 0. Sorry, I can't plug in 1, right? We're going to 1. So if I plug in 1, I still got 0 over 0. So this didn't help that. But now I'm going to multiply by 2 plus, and this is the conjuring trick, right? And that's going to give me the limit. Can I fit this in here? This is going to be a gargantuan expression, isn't it? Well, on the top, I'm just going to compute the difference of squares, right? And that's going to be 4 minus, in parentheses, 2x plus 2, right? So what have I got on the bottom? And this I'm not going to multiply out. I hope that's going to be all right. But yeah, I've got all of that, right, with a 2 plus square root of 2x plus 2 times, maybe I should multiply this out. I keep saying I'm not going to, and then I do. X minus 1. So you got a big train wreck of terms down there, right? Multiplied. So on the top, obviously, I have that. Oh. Yeah. Do I have what I want on the top? Yeah, I do. Do you see it? 4 minus 2 is 2. So we have 2 minus 2x, which I can factor out the 2 there and get 1 minus x. Or I could factor out a negative 2 and get negative 2 times x minus 1. All right, that's what I'm going to write. Limit as x approaches 1 of negative 2 times x minus 1. All right, and then I got all this stuff here. Do I have to rewrite it? Jeez, it's a lot of writing. And I've got a 2 times square root of 2x plus 2 again. And then I got an x minus 1, right? So that's why I factored out the negative 2 on the top. So I could see that instead of 1 minus x, I've got x minus 1, which is literally the same as the factor down here. Okay, so those cancel out. And that's what's going to 0, right? So we cancel 0 over 0. And now I think I can just plug in 1, right? Yeah. What do we got on the top? Take the limit of the top. Well, that's a constant. On the bottom, 2 plus 2 is 4 times 2 is 8 times 2 is 16. So negative 1/8. What's the equation for the tangent line? Well, it's going to be y minus f of 1 equals f prime of 1 times x minus, the same thing as last time, right? And so we know that f of 1 is 1/2. So y minus 1/2 equals, we know this is negative 1/8, and this is x minus 1. So it's got a small negative slope. What does the graph of this thing look like? Well, the domain of this function, x has got to be bigger than negative 1, right? At negative 1, it's got a vertical asymptote, right? So we're coming down off a vertical asymptote. At 0, we're going to have 1 over the square root of 2. It doesn't have any x-intercepts, and so it's just going to approach the horizontal asymptote y equals 0, right? Because as x gets large, that's going to go to 0. I don't think it wiggles around, so basically we got a graph that looks like this, right? What do we say the intercept was? 1 over square root of 2, or square root of 2 over 2, if you like. And we say it's got a vertical asymptote at negative 1. And then It follows this is the x-axis and the y-axis as usual. Oh, sorry. So where's 1? I don't know. I didn't scale the x-axis, did I? F of 1 is a half. This is about 0.7. Right, so 0.5, if I scale them the same, is going to be about here. And the equation for the tangent line is going to look like this, right? So you see that basically we're kind of in the ballpark, right? Because we have a negative slope, seems to be fairly gradual. So this is the point 1/1/2, right? That's what the point of tangency. And the tangent line, whose equation is here. Do we want to solve for? Do we care? Y equals negative 1/8 x. That's this mx, and this is 1/8 plus 4/8 is 5/8, which is about 0.6 something. So it's a little less than 0.7. So that, everything seems very reasonable. Okay. Well, let's jump back. Do I see any questions? No. Okay.
I have 2 questions.
Go ahead.
Okay, so 1, are you choosing x to be 1 just because it's like the easiest number to compute, basically?
No, they give that in the statement of the problem.
Okay, so the number to choose is given, like, and what does that depend on? Like, what point we want to see the tangent line at?
Yeah, and it should be in the domain, right? So that there is a tangent line. But,
okay.
Yeah, you see here they have.
Okay, so A equals 1.
And all these uses to find f prime of A for the given number A. So we went a little further. We found the equation for the tangent line, and we drew a graph that shows that it makes sense. But that's kind of the rule at 3 at work, right? Well,
right. Okay.
We didn't do a lot of numerical evidence, but enough to draw a reasonable graph.
And then my second question is, can you repeat again why you're choosing to do f of x minus f of 1 over x minus 1?
Sure, that's let's go back to the picture. Good question.
And then I guess I have one more. And then as for the limit as x approaches number, like whatever number it is, that's also depending on what's given, correct?
Mm-hmm. Right.
That depends on the x value that's given in the problem.
Right.
Okay. Okay.
So on the graph, so our goal is to find the slope of the secant line. So what we do is we draw a secant line. Did I say secant? We want to find the slope of the tangent line, right? So here's a secant line, passing through x f of x and 1 f of 1, right? So that blue line is the secant line. The secant line is as x approaches 1, this line is going, this point is going to move along the curve towards this point, and then we'll just have, if the closer x is to 1, the better that approximates the tangent line, and in the limit, it is the tangent line. Right. That's what this chapter is all about in a way. Right. So with that in mind, let's see, usually towards the end, there's some more interesting problems. Let's see, they got, numerical, like I say, the rule of 3, numerical evidence, graphical evidence, and algebraic evidence, right? Symmetric difference quotient. Oh, this is kind of nice. Remember when we were talking about approximating the tangent line with data, and we said, you can average the slope of the line, through your point and the point before your point, and with the slope of the tangent line through your point and the point after your point. But then let's see, this is kind of bright back here, isn't it? That is approximated by just taking the slope of the secant line or the point before your point and the point after your point, skipping over your point, right? And you actually get a better approximation. So that's what's happening here, right? You're taking, if you want the f prime of A, you can take f of A plus D and subtract f of A minus D. So that's the point after minus the point before, and then the difference in inputs is going to be 2D, right? And yeah, that's kind of a good way to go oftentimes, right? So yeah, that's the very last problem in here. So with that in mind, maybe let's just take a few minutes to introduce the concepts, because some of you may want to jump ahead into 2.8, which introduces the idea of the derivative function. So this is what we left off with last time, right? That we can find the slope at a point. But what if we change our point of view and let that point vary? Instead of having the slope at a fixed point, take the slope at an arbitrary point x. And so we can do that again in two ways. We could say x plus h and x are the two inputs, and so there's the corresponding difference in outputs divided by the difference in inputs. Do they also show the other one here? I'm scrolling. Other notations? Yeah, right. So this, the limit of the secant line, the secant line, we use the Greek delta for difference in y coordinates divided by, the difference in x coordinates. But the notation for the instantaneous rate of change, the slope of the tangent line, we say dy by dx. Well, that's what they say in England. They say dy by dx, and here we can say just dy dx. We don't necessarily say the word by. Dy divided by dx, but that sounds kind of long-winded, right? So dy dx will do the trick, right? So this is the Leibniz notation. And so the slope at a point x equals a, you draw a vertical bar here and say, yeah, we're going to compute that at a. And that's a synonym for f prime of a. The vertical bar means evaluate dy dx at a. So dy dx is the same as f prime of x, right? It's the slope of the tangent line at any point, or it's the derivative function. So they give you an example of the absolute value. Where is it differentiable? Well, it's not differentiable at 0, right? F prime of 0 does not exist. There's no tangent line at 0. Yeah, right? See, look here. So the derivative function looks like kind of like the Heaviside function, a little bit different. It's got a step at 0. It jumps from -1. The slope before you get to 0 is -1. The slope after 0, +1. And at 0, there is no slope, right? It doesn't make sense to draw a tangent line at a point, right? It's not smooth there. It doesn't have a tangent line where it's not smooth. So both continuity and differentiability are desirable properties for a function to have. Well, it depends on who's doing the design. That's a judgment call. The following theorem shows, I mean, maybe you like pathology. You're sort of perverse and you like things to misbehave. It's more interesting. The following theorem shows how these properties are related. So if f is differentiable at a, then f is continuous at a. That's true. So differentiability is sort of the polysyllabic word for saying it's differentiable. Then, well, the concept of being differentiable is called differentiability. And differentiability at a point implies continuity at a point, right? You can't have a jump discontinuity and be smooth, right? However, continuity does not imply differentiability. Do you see that? Right here. Perfect example. It's continuous at 0, but it's not differentiable at 0, right? The derivative does not exist. So yeah, differentiability implies continuity, but the converse does not imply. And so here's a little proof of that. Maybe we can go over that on Monday. The converse of theorem 4 is false. Note, this is like in heavy purple or red or whatever that is. We're just taking a quick tour through this. How can a function fail to be differentiable? Well, one way is to have a sharp corner. That's not the only way. Look what, yeah, well, this has kind of a sharp corner, but notice that this one is smooth, right? So this has a vertical tangent, right? The slope of the tangent line is a vertical line. And you can see that the function can be smooth and have this property where the tangent line is vertical. That means it has no slope. That means that the derivative does not exist, right? So these are three ways. Let me count the ways that f cannot be differentiable at A. It can have a corner, it can have a discontinuity, or it can have a vertical tangent. Okay, so, and you know, again, here's this idea, if you're differentiable, then you're smooth. If you zoom in on a smooth curve, it starts to look more and more like a straight line. No matter how deep you zoom into a corner, it's never going to look like it's not a corner, right? So some corners are, something that look like corners are actually not corners, because if you zoom in enough, you see, oh, that's actually smooth there. It's blunt, right? It doesn't have a sharp point, it's rounded. So it's hard to tell sometimes just by looking at the graph whether it's smooth or not. So higher derivatives, so this is called the differential operator here, right? So this is not a derivative. This says take the derivative of what follows it. So this performs an operation on the thing that follows it, right? So dy dx is a derivative, right? And the derivative of the derivative is what this is saying. So if we apply the differential operator to the derivative, we get what's called the second derivative, the derivative of the derivative. The derivative function is a function, right? So you can take the derivative of that function, derivative function, and you get a second derivative function. And you see why the notation is what it is here, because, you know, this is actually not multiplication, but it kind of looks like maybe it is. So this is a shorthand, right? It can be confusing notation, right? Because it makes it look like it's d squared. It's not d squared, really. This is a notation for the second derivative, right? So that can be a little bit confusing. So if we have the first derivative is 3x squared minus 1, then we compute the second derivative. Notice that's two primes, right, next to each other. So prime prime is second derivative. The derivative of the derivative is the second derivative. And we can go ahead and compute that. So you get the function itself is a cubic, its derivative is a quadratic, and the derivative of quadratic is a straight line. Oh, interesting. So how do coefficients affect graphs? Okay, there's a little exploration there. Third derivative, yeah, you can just keep going. There's no stopping you. So that's denoted, as you might expect, like this. How are we doing? We're at 8, we got 1 minute left. And so they give you some examples of, you know, looking at graphs, and then we get into the exercises. So there you go. You can have at all the remaining homework exercises, which there's probably too many. Sorry about that. I try not to make too many, but yeah, some of you don't have enough, right? So if you don't have enough, there's more. Where? Well, I posted in here. You can see, you won't see these, which are the solutions. I'm thinking they're the solutions, but you know, this is a spring 16, presumably. It's a little, yeah, chapter 2 test, sure enough. Okay, I was worried that it wasn't the chapter 2 test. And so you get some numerical data. And so look at these. We'll talk about these on Monday, and we'll have some time to review also before the exam on Wednesday. So any questions about anything before we bid adieu?
Yeah, Professor, so do you recommend like printing this out and kind of working through them before Monday's class?
Sure.
Okay.
Yeah. Yes, and see if you can work them out, right? If you can't work them out, what do? Well, try to articulate a clear question that if you had the answer to that question, you would know how to figure it out, right? So that means, you know, articulate, why are you stuck? What is it that's holding you up? And sometimes just by articulating that, you will then have, you know, the problem in your mind, and you'll wake up out of a deep sleep and say, oh, that's what it is. So good luck. Yeah, I hope that works for you. Yeah, study. Any other questions?
How is the test gonna work? Like, is it gonna be over web design or?
Well, we had a little discussion about this at the beginning. I don't know, maybe you missed that. We have less people than we had at the beginning because it's now after start time. But I said that we would resolve that question. You know, it could be a mixture of WebAssign problems with written problems that you have to show your work. Yeah, or I could make it a MyOpen math test, which is very similar to WebAssign. And I think WebAssign, I can actually do this too, where, you know, just write out your answer and upload your work as the answer. So I just need to investigate all that. I'm not as familiar with WebAssign as I should be, I guess. So yeah, stay tuned. Monday we'll talk more about that. But you might anticipate that it looks just like this, and you write up. So notice what the instructions say here. Write all responses on separate paper. Show your work in detail for credit. No calculators. Well, yeah, I'm not going to be able to police that. So maybe I should say, you know, this one you'll need a calculator because it's really not reasonable without one. You know, maybe that's the way to compensate for, you know, all of these things, you know. So that's why I want to see your work, right? Because honestly, if you know how to use a computer algebra system, you know, so why bother with learning how to solve problems? Because, you know, now artificial intelligence can solve them all. Well, somebody's got to train the artificial intelligence, right? You know, in order for a scientist to make sense of what they're doing, I mean, this is one of the things I worry about with science, that they're so reliant on, you know, technology that they've really lost sight of what science really is. They're really not doing science anymore. It's just sort of herd mentality, if I might say. Yeah.
So should we not be using calculators to solve this practice exam?
You know what you do? Yeah, try to do it. Yeah, this is designed to be done without calculators. So go ahead after you have the solution, use a GeoGebra or something like that to verify that, yeah, I want to, you know, sort of delve a little bit deeper into this with the technology and verify that, yeah, what I think is happening, or maybe get a bit greater appreciation of what is happening, you know.
Yeah. So then using calculators for the exam is the topic that's still undecided, right?
Yeah. I honestly, I just don't know what the hell to do. I mean, I can't walk around and say, oh, you're using a calculator. I know some teachers have like proctoring software. I really object to that. I don't like it at all. I mean, your home is still a private place as far as I'm concerned, even if you're enrolled in a course where, you know, it's the same reason I don't make you show your picture, which nobody is showing their picture. Very few people are showing their pictures. So I get it. That's fine. Whatever. I kind of miss seeing people's faces and stuff. All right. Okay, so we'll talk more about all this on Monday, and I'll be in my office tomorrow, 9:20 to 10:20, sometimes a little late to the 9:20 slot because I'm still in the previous class, but hang out, I'll be there. And Friday from 10 to 11, I believe. Okay, so if you want to see me at those times, I think did I post a little thing about how to do that? I thought I had. Let's see, it's something called task, I think. Week 2, week 1. Was it in week 1? Oh.
I
haven't been. Yeah.
Yeah, I think you did at the very beginning of the semester.
Yeah. Is that still? I don't know how to find it here.
It should still be there if you had posted it.
Yeah. So let's see if I go to pages. Maybe it's a page. View all pages. Is there something called task? Is alphabetical, right? There's nothing under T. I think task was different. So this was like how to or something. Yeah, how to.
Yeah, it was like a how to reach my office hours. And I think
Yeah.
you done it in an announcement.
Okay. You know, I know where it is. I'll get it. I think it's in the other class. So I'll post it over here under this week's module just to be sure.
Okay, thank you.
All right, you bet. All right. Good night, everybody. Have a pleasant evening.
Good night.
Can I ask you a question?
Oh yeah, go ahead.
So because I joined late, I have like a couple of like math assignments from like chapter 1 that I haven't done yet, and I cannot do them unless you extend them. Do you want me to do them?
I thought I had extended them for you, Travis.
Yeah, well, they still say the same dates.
Oh, so I extended them, but not far enough. Okay.
Well, when I go to my past assignments, it still says the same date on it. It still says the due date on them.
Oh, all right. Yeah. Note to self, fix that. Okay, it takes a little while, but I'll get to it.
Yeah, no problem. I just want to make sure that you want me to get everything
Sure,
done.
I'll do that this evening. Okay.
All right, perfect. Thank you.
All right.
Appreciate it.
Okay, that'll be a wrap then, and have a pleasant evening. See you later.